Welcome to Handmade Data Structures in C. I'm your host, Christopher Dumas, and today I'll be covering binary trees. Binary trees are a pretty interesting data structure for two reasons. The first reason is that they're good at sorting and searching, and the second reason is that they're essentially just linked lists with just a few more behaviors on top. So, what is a binary tree? Binary trees are very similar to linked lists. They are composed of nodes that have links to their parents and children. Unlike linked lists, however, these nodes have two children, not just one, a left node and a right node. The reason they do this is so that you can actually sort the nodes. So for instance, if I had the numbers 1, 2, and 3 and inserted them in order 2, 1, 3, I would insert the 2 as the root node because it comes first. Then, when we get to the 1, we'd put it to the left because it's less than the root node. And when we get to the 3, I'd put it to the right because it's greater than the root node. The benefits of binary trees, however, come from when you have more data. So let me insert some random data here. So let's start with 10, right? And then insert a 5. And then let's insert a 15. And then let's insert a 13. Right? Because 13 is greater than 10, but it's less than 15. Because you can't replace a node, right? You can't put the node where there's a node already. Let's insert a 16. Alright, so you got a pretty hefty tree here. When you're searching your binary tree, if you can determine whether what you're looking for is less than or greater than the current node that you're on, you can essentially cut off half the tree. So for instance, if we're looking for 1 here, right? First, it's less than a 10. So we can just cut off this entire part of the tree. We don't need to look there. And then, it's less than 5, so we cut off this part of the tree. And then it's less than 4, so if there's anything here, we cut it off, and then we find it. Notice, however, that the order and the placing of nodes in a binary tree is heavily dependent on the order you place them. For instance, if I placed in a tree 1, and then a 2, and then a 3, we just end up with what's essentially a linked list, and we lose most of those benefits. That's actually where red-black trees come in. But we're not going to cover those today since they're very complex. Look for them in a future video. Anyway, so searching is pretty efficient in a binary tree. Alright, now that you've got a pretty intuitive understanding of what goes on in a binary tree, let's actually codify this with some code. So let's head over here, and so I've already built up what you'd call a test suite, essentially, to make sure that we have something to actually test our implementation against. So, we have a method for printing out a tree. This prints them out sideways. So, for instance, this is a full tree here, and, 2 is the right node of 1, and then 6 is the right node of 2, and so and there might be odd spacings here because each node might have its own children. So for instance, this is slightly confusing here. 12 is actually the right node of 8, and then 9 is the left node of 12, and then, right node, and so on. So that's that. And then what the mate function essentially does is it inserts and finds and deletes a couple nodes and prints out, the tree in between, and then it, deletes the final node, adds a node, and I always run my C programs with valgrind, as you'll see later, because it just makes sure we don't leak any memory or do anything particularly dubious. Notice this warning here is something that actually is generated by the GitHub published version of my code. Alright, so we're going to start in the header file, and what you want to do is, so actually, before I start, An interesting thing that I decided to do here is because the binary tree needs to have information in order to compare and check for equality between nodes, and we still want to use void pointers so that the binary tree can be used for any type, we actually need to pass in function pointers, which are essentially callbacks, for the tree to call to compare and check for equality between nodes. So I decided to create a wrapper structure that keeps track of all that, so you don't need to keep passing that in to every tree-related function. It's not necessary, but it's just something that's nice. We didn't really need to do this for a linked list because the linked list didn't have much metadata that was difficult or annoying to pass in. It obviously had the size of the data, which we're going to be keeping on the binary tree wrapper struct since we already have it, but just the length of the data isn't something that would necessitate a wrapper struct. So let's start with the wrapper struct here. So we're going to call it binary tree. That's for pure internal use only. And then the external name is binary tree _ t. And it's going to have a B node, which is a binary tree node, and a pointer to the root, and then it's going to have a size t data len and the function pointer. So comp t comp and equal t equal. I'm going to define the function pointers. So a function pointer takes the form of a regular function declaration. So for instance, it could be bool foo takes a void x and a void y, with one difference. Instead of a regular name, right, we want to define it as a pointer. So if this was a variable, we just put the star in front. But that would actually be considered part of the return type. So we need to put parentheses around the star and the name. So this is actually a valid type, and when we do type def of this, instead of specifying the name after, we actually specify the name inside the function pointer type, since there's got to be a name there anyway. Alright, so, and the equality looks exactly the same. We're going to use the bool type, which is part of the C language since the C 2011 standard. You don't see it around a lot, but I feel like it helps with code clarity, so there's really no reason not to use it. I'm also going to include string.h, so I get mem copy and size t. And I'm also going to implement or define the B node structure and type alias it to B node t. And the node obviously has a void pointer to its data, as well as a B node pointer to its parent, its left child, and its right child. Alright, now that that's defined, let's work on what functions we're actually going to need. So first of all, we're going to need a way to make a new binary tree. So that's going to be binary tree t, pointer obviously, new tree, and we're just going to copy over all of these arguments here, since they can just stay exactly the same, since this is just an initializer. And that's that. Then, unlike linked lists, once again, since we have a wrapper, we're never going to need to create a bare node. So instead of having a new node function, I'm going to just wrap in the stuff that relates to making a new node into the insert function. So again, the insert function is just going to take a tree, so binary tree t, and some data to insert. Notice that we don't need to pass the len because we've got a wrapper. Also notice that insert returns void because we've already got a pointer to the root in the wrapper, so there's no need to return a new root or a new place to add. We're going to need a delete function with fairly similar arguments, although we're actually going to require the person to pass in the actual node they want to delete, just to simplify things. we're going to need a find, which is actually going to return the node. So just like this, and then take the tree, obviously, and instead of looking for a specific node, because if we already had the node, why would we need to find it? We're going to use data. Then we're going to need a way to free a tree. And that's it. Notice that the best way to implement a lot of these things is through recursion. So we're actually going to need to define some internal functions not defined in the header function to get this to work. So these are actually more like wrapper functions. If you need an explanation of recursion, this is not the tutorial to look for it from, but I'm going to explain it real quick. Essentially, how recursion works is you have a certain function, right? We'll call it fun, and you give it an argument of 100. Well, if it wants to add up all the values up to 100, right, it would count down, and it would just call itself on 99, and then take the result and add 100 to it. And then that function would call fun 98 and call that on plus 99. And when we finally get down to fun 0, what's going to happen is that it's going to return a number, namely 0, instead of calling itself. That's called a base case. And so then the compiler would work its way back up to the beginning and return the final result. Okay. So we got that. Now let's just copy those function prototypes into the C file, just like that. We're going to need to include the header file, obviously, as I covered before. Okay, so to create a new tree, we just need to malloc chunk of memory the size of a tree wrapper, just like that. And then set the root to null, so we don't got anything there yet. Set the data len to data len. Set the comparison to the comparison. Set the equal to the equal. And return the wrapper. So as part of insert, we're first going to initialize a new node. Right, so malloc the correct amount of memory. We're going to then malloc inside of the node's data the size of the data from the tree. And then memcopy. Also notice over here you can get documentation on any C built-in functions by doing man and then the name of the function. So I've done man memcopy and I get to see the argument order right here. So the destination comes first, so node data, and then we have the source, that's data, and then we have the size, that's tree.dataLen. Alright, and then instead of returning that, right, because this is not a new node function, we instead call insert node on the tree's root node and the new node, and we want to pass in the tree's comparison and actually just the comparison operator. And then we're going to define insert node, right? And it takes a node as the root. It takes a new node to insert. And it takes a comparison callback. Alright, so insert node is pretty simple. What we do is so this expects comp to return true if the node's data is less than the root's data. So it returns true if we need to put this node to the left of the root. So if root left is null, then we've got an easy job of it, right? We just need to set root's left to this node. Otherwise, we just want to call insert node and make the left node the new root, right, to restart our search. Pass in new, pass in comp, just like that. Otherwise, right, if this isn't true, we want to do that on the right node, just like this. So actually, let's do find first, because find is pretty simple and similar to insert here. Find is actually going to call find node on the tree's root, and with the data, and with the comparison, and the equality callback operators. Reason being, again, we need to recur, and we don't want to create a new binary tree wrapper every time we recur so that we can just call find directly. So instead we need an inner function called find node. So we're going to return whatever that returns. So this has got to return a B node. We need a root, we need a data, we need a comparison, and we need an equality callback. If the current root is null, well then there's nothing to find, right? The root isn't data, and it's also not going to have any children to search, so we return null in that case. Otherwise, right, if the comparison says we need to go left, and the left, right, we go left, find no root left, and if it says we need to go right, we go right. Right, and then up here, if the root's data is actually equal to what we're looking for, we just need to return the root, because we've found the node we want. Alright, so now we actually are on to delete here. So for delete, we're going to do something pretty simple. I have a more complicated implementation up on the GitHub that you might want to study that actually chooses if the node we're deleting has a single node child, then it can put that child back into the tree. Otherwise, if it has two nodes or no node, it doesn't do that. That's actually in preparation for red-black trees. So go ahead and look at the GitHub code if you're interested in studying that. For this purpose here, what we're just going to do is we're going to set the parents. So if this node was the parent's left node, we want to set the parent's left node to null. And if this was the parent's right node, we want to set the right node to null. And when we're done that, we just do a free node. So notice that we've only got free tree here. This is going to be a pretty similar situation because we need to do some recursion. So just like that. And I'm actually going to put a prototype up here so that we can define free node with the main function that uses it, but also use it in delete, which needs to come first. So then, if root is null, then we don't need to free it, so we just return. Otherwise, we want to free the left and free the right, and then we want to free the current node's data and the current node itself. And then for freeing a tree, we're just going to free the root node, right, because that'll free all the nodes below it, and then we just free the tree itself. Oh, one other thing. When we're initializing the node, we want to set the left to null and the right to null, just so there's no uninitialized memory bouncing around. One last thing before we move on to actually testing. We want to, if there's no root node in the tree, right, so if the tree's root node is null, we want to make the tree's root node whatever node we're inserting. Otherwise, we want to do a regular tree-based insert. In the same vein, one last thing we need to do is when we insert a node, we actually need to set its parent, right, because we were using the parent a bunch of times earlier. So like so. And just like that, it works. Now let's take a look at what's actually going on. The for node was quickly found by the find function, and we get this little tree here, which is right up here as well. And then, we delete the node of 4, and notice 8 and the 3 are gone. We find the 10, right? When we delete it, 8 and the 11 are gone. We found the 12, delete that. We added the node 99. And here's the reason I use Valgrind. It's really good at giving hints to make sure that you don't miss anything. So in this case, everything's freed correctly. I'm going to go through the code one last time. Just give a general summary and overview. Something that I forgot to do in the last video in this series. So we got a node structure with pointers to its parent and its two children, a lot like a linked list. We've got a alias for two function pointers, which are ways of passing a function, any function, to somewhere else. So for instance, this is actually used up here, right? So we have an int comparison function, and we pass a pointer of that int comparison function to the new tree. And so the tree now has a way of jumping to that, even though it didn't even know that existed when we defined the tree. We've got a wrapper function just to keep track of some metadata about the nodes. Totally not necessary, but very convenient. We have a way of creating a new tree. And we have an insert function that uses the tree wrapper and some data to create a new node using the tree wrapper and this metadata and the data that you pass in, and then finds a way to add that to the tree. We got a delete function, we got a find function, and a free function. I hope this was educational. I hope this was helpful. I really enjoyed making it. It actually took quite a few attempts. I was able to write this correctly in one try off camera, but when I tried to re-implement it on camera, there were some bugs. I actually decided not to include the more complicated implement of delete because of that, because apparently I wasn't able to successfully code it while the camera was watching me, unfortunately. That's just how life goes. The code, including the more complicated delete function, is at github.com/ChristopherDumas/cbinarytree. I'll put the link right here, and catch you guys in the next one. I hope you enjoyed.